Alright, so we are going into Chapter 2. Chapter 2 is going to be dealing with logic, which is a very important part of math in general, and a very important part of geometry when we get into proofs. So this chapter gets us started with proofs. Before we get into actual geometric proofs, we need to learn about logic, and that's what these first few sections are going to be about. Before we get started, we're going to go ahead and do a quick warm-up. Just so you know, the warm-up is a part of your notes. So make sure you're writing these down as your notes. Don't skip it. Write the statements. Don't just write the word, because you can't use just the word to review later on. Anything that shows up in a warm-up, I have no problem putting on a test or a quiz, just so you're aware. Alright, so this first warm-up is just vocab words from Chapter 1. And again, you can go ahead and pause this and write this down and kind of complete this yourself, and just double check your answers as we go through them. Okay, so number 1, it says blank points are points that lie on the same line. Just to give you a quick reminder here, we got a line, and these are points that lie on that line. And there is a name for that. That name for that is collinear. So number 1 is collinear. Number 2 are points. Blank points are points that lie on in the same plane. So here, if I had a plane and I took 3 points that lied in that plane, these points would be called coplanar. A couple things about coplanar, collinear points. You know, points that are collinear in a way are coplanar in the sense that they lie in the same plane, but if you're actually going to label a plane, I just want to make sure, because this is something that we had on our quiz and there were some issues with it, just make sure you understand that if you can't label a plane ABC if the points are on the same line. Yeah, they are coplanar in the sense that they lie on the same plane. A, B, and C are all on the same plane. However, you know, in order to label a plane, you need 3 coplanar points that don't lie on the same line. So in this case, these are coplanar points. They don't lie on the same line, which means they're not collinear, so I can label this plane ABC. Okay, I could not label this ABC, however, because those 3 points are on the same line. So technically, there's a ton of different planes that can shove through this. I mean, you see how you got the plane that's on the screen now? Could try to draw like a vertical plane here as well. You see how it would go through there? There's more than one plane that would fit on those 3 points. However, here, there's only one plane that fits those points, and there we go. Alright, but that's 1 and 2, collinear, coplanar. Number 3, the sum of the measures of 2 blank angles is 90 degrees. Okay, so you got to remember 90 degrees, we're dealing with either complementary or supplementary. In this case, this would be complementary. So we got complementary angles are 2 angles that have a sum of 90 degrees. So again, that's a warm-up. Again, you know, in addition to this, I mean, there are other vocab words, so this is just a quick glimpse. A reminder that you still need to know the vocab words from Chapter 1. We're going to be using those as we do proofs. As part of our knowledge base is definitions, postulates, and then we'll be proving theorems. Alright, so moving on to our actual lesson here, we're going to go over again 2.1, which is using inductive reasoning to make conjectures. So we got to know, obviously, as we go through our lesson, what is inductive reasoning. If we don't know inductive reasoning, we can't make conjectures. I mean, these kind of go together. So you need to know what inductive reasoning is, you need to know what a conjecture is. And part of inductive reasoning, or proving things to be false, is finding counterexamples. So we need to know how to find counterexamples to disprove conjectures. So that's our goal. Again, same thing, I would write down the lesson goals if you're in Patrick's class, and I'm checking the notes. I'm going to be checking for the things that I'm telling you to write down. So if I tell you to write something down, you probably should be doing it. Okay? It's important to have good notes, not just a couple quick examples written on your paper. Put some effort into it. Okay. So here we go. Let's get started. We're going to do some real easy patterns here. So if you're writing this down, we're going to do a few different patterns in a row. So again, find the next item in the pattern. Those are going to be the directions for the next few slides here, so we don't have to keep writing that down. All right, so what we need to do is look at what the list that we're given and find a pattern. So if you look here, we got January, March, May. Well, it looks like we're skipping. We skipped February. So I'd be like, February, where'd you go? I skipped it. Okay. March, April, where'd you go? We're skipping it. So the next term, we're going to skip June. Where'd you go? And we're going to have July. There's your next term. Okay. Now again, this pattern may be we skip a month, skip 2 months, skip 2 months, then skip 3 months, skip 3 months. We don't know that July's next. What we're doing is we're making an educated guess. Okay. And again, it doesn't mean it's true, but you know, it seems to be true based off the information that we have. Okay. That's going to be important moving forward. Next pattern, we have 7, 14, 21, 28. This is actually like an arithmetic sequence that you learned in Algebra 1. And here we're adding 7 every time. So we want to keep adding 7. Again, the difference between this and an actual arithmetic sequence, in an arithmetic sequence you are told that you're adding 7 every time. You're told that this pattern is consistent. Here we're just making an observation. They look like they're adding 7 every time, but maybe the pattern changes later and we don't know that. But we are going to assume that 35 would be next, because based off the information that we have, we're going to keep adding 7 every time. Not done with the patterns yet. Next pattern, we're going to use some stuff that we just did in Chapter 9 here. I'm going to just follow this point, just so you know. I'm going to see how is that point moving. Well, it looks like this point that's on the top of the triangle, it looks like it got rotated. So if we go from here to here, looks like we went 90 degrees in a counterclockwise direction. And if you follow it again, it looks like we're going 90 degrees in a counterclockwise direction again. You see this point, it kind of went over here, kind of went this way, and then it went that way. Okay, so if you follow that pattern, we should be able to draw our next triangle. So if I rotated it again, again I'm following this point, it went here to the left, went to the bottom, now it's going to go to the right. Again, we don't know if that's true, but we're assuming that it's true based off the information that we have. Okay. Next one, find the next item in the pattern. Here we got 0.4, 0.04, 0.004. So it looks like we keep adding a 0 every time. So this next item should be 0.0004. And we're just knocking out these patterns left and right. This shouldn't be too hard to see these. There are some tricky patterns though. They're not always as simple to find. I'm just kind of setting up inductive reasoning at this point. And I want to keep talking about the conjectures that we make, how they're not going to be proofs, because we don't know that the next term is 0.0004. We are assuming based off the information that we have in front of us. That's all we can really do at that point. Alright, so again, what we are doing is some inductive reasoning. Now, yes, you should write this down. Am I expecting you to write all of this down? No, not necessarily. Okay, but you want to write down the definition here for inductive reasoning and the definition for conjecture, because these are the things that we are doing, so you're going to want to make sure you make note of it. This is not the only type of reasoning we will use in this chapter, so you want to make sure you know the difference. So definitely write this one down, and then when we do deductive reasoning, you'll be able to kind of talk about what's different about them. So inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. So again, we were looking at a pattern and we noticed the pattern, so we were able to use inductive reasoning to make an assumption of what that next term was. Well, a statement that you believe to be true based on inductive reasoning, that is called a conjecture. So the answers we were coming up with were our conjectures. So like again, if we were going 2, 4, 6, and you want to know what's next, this is your conjecture. And the inductive reasoning is we would say, well, it looks like I'm adding 2 every time. So there's your inductive reasoning. Okay, so again, just definitions that you want to make sure you understand. Write down what you need so that you can look that up later and it's easy to spot. Okay, if you just write down inductive reasoning, conjecture, you don't even write a definition, then don't waste your time. Okay, but you need to do it the right way. Alright, so now we're going to make some conjectures. This one we have to kind of create the pattern ourselves if we don't know the answer, so I'll go ahead and give you a couple examples as we do these. So to get started, it says the sum of two positive numbers is what? So here we want to come up with some patterns that we can use, or some examples that we can use to create a pattern. So I'm going to take some positive numbers and add them, like 1 plus 2. 1 plus 2 is 3. I can go 1 plus 7 is 8. I can go 7 plus 9 is 16. But the one thing that, this is, again, I'm giving you some easy ones here. The one thing that you're going to note from this is that the sum of two positive numbers is always positive. And that's a pretty simple one, but again, we're making conjectures based off of some patterns. Now, we have not proven this statement to be true just because we came up with a few examples. Okay, there could be, and I'm trying to get ahead of ourselves a little bit so you understand where we're going. I could, if this was not a true statement, I should then theoretically be able to come up with an example that showed me two positive numbers being added and me getting a negative. Now, that doesn't exist in this case because this does happen to be true. I'm just letting you know we have not proven it with this statement. Okay, that's where we're heading. You don't need to write that down now. Next up, the product of two odd numbers is what? So I'm going to multiply some odd numbers. 1 times 3 is 3. Okay, and again, once I multiply some odd numbers, I'm going to look to see if there's a pattern. So I'll go 7 times 5 is 35. I can go 11 times, let's go 9, is 99. And it looks like when you look at all three of these, I always get an odd number. So I'm going to say the product of two odd numbers is odd. Again, I haven't proven that. We don't know if that's true or not. All I really know at this point is that based off the pattern I have, I could assume that it's always going to be odd. Again, it's not proven, but it is true, by the way. Alright, so the next one we're going to deal with is we got this chart, average whale lengths. Obviously I'll give you a second to write all this down so you can get the chart, and we want to make a conjecture about the lengths of male and female whales based on the data. So as we're looking at this data, what you'll notice is a relationship here between the females and the males. And it looks like here, if you kind of take a look, we got the males that are a little bit less than the females when at 49 feet for the females. And the females are 51 feet, the males are less. Here the males are less. Here the males are less. Here the males are less. And here, well, the males are greater. But again, if you're looking for any other patterns, you're really not going to see it. These numbers kind of jump around a little bit. And then you have the length for the males, they kind of jump around a little bit. The only semi-consistent thing we have, if that didn't exist, we would know for sure, is that the average length of the male is typically going to be shorter than the female. So if you want to make a conjecture, again, you haven't proven anything, you're just looking at the data and you're making a general assumption. So you're going to say that, males are generally shorter. I'm talking about males. Okay, are generally shorter than females. Again, with anything, when I say generally, it's mostly true. Usually males are shorter based off the data. Just like saying that, with humans, that girls are generally shorter than guys. There are girls that are taller than some guys, but overall, most of the time males are going to be taller, and that's just going to be, again, a general rule. You can't make a broad statement about something like that, because there are always going to be situations where that's not true. So it's not, again, a proof. I haven't proven that males are always shorter. based off this data. Actually, in itself, it has what's called a counterexample. So going into counterexamples, what you want to do to show that a conjecture is always true, you must prove it. And again, that's something we haven't done yet. We just made conjectures and that's it. We haven't proven anything yet. Obviously, that's what this chapter is about. It's about getting us into a situation where we can prove. We just haven't done it at this point. And so to show that a conjecture is false, you have to find only one example in which a conjecture is not true. So this is going to be our counterexample. And we're going to start finding them. It's one of our key words, which is why I'm circling it. So we want to have that definition. Again, a counterexample can be anything that proves it to be wrong. Depending on the situation, it can be a drawing, a statement like a sentence, or a number, or a situation that involves numbers. So make sure you get that definition, then we'll move on. Okay, so if we're doing the inductive reasoning method, what we're doing and what we have been doing is we're looking for a pattern, number one. That's what we did on the first examples. We looked for a pattern. Number two, we made a conjecture based off of those patterns. Number three, we're going to need to prove the conjecture, or we're going to need to find a counterexample to show that it's false. Again, if we're trying to prove something to be true, what we're trying to say is that it always works. So if we find one time where it doesn't work, then therefore it doesn't always work. So this is going to be our process that we need to follow using that inductive reasoning method. Alright, so here we're going to, it's a lot easier to prove things false than it is to prove things to be true. So as you'll see here, we're just going to focus right now on finding counterexamples. So we're proving something to be false. So show the conjecture is false by finding a counterexample. So here we go. First up, for every integer n cubed is positive. So I need to come up with one example where that is not true. In other words, what I need to find, so the counterexample, what I'm looking for is I'm looking for n cubed to be negative. That would prove this conjecture to be false. So that's my goal. So let's go ahead and find it. And again, you can come up with your own number. You can pause this before I write it, and you can, I got it right in my head here. But here's going to be our counterexample in this situation. I'm just going to say n equals -3. Okay, if n is -3, that is an integer. An integer is any number, by the way, an integer, I'll throw some up here, like -3, -2, -1, 0, 1, 2, 3, and so on. So as long as I'm using an integer, I should be fine. Here's an integer. Now n cubed is -3 times -3 times -3. Again, that's what you do when you cube a number. You multiply it by itself 3 times. Put two of those together, that's 9 times -3, and I get -27. Now, some notation that you're going to see me use is this notation. Let me put it off to the side here. It's going to be 3 little dots. You need to write this down, and this is going to be something that I'm going to use a lot, so I want to make sure you know it. These 3 little dots, they mean the phrase therefore. I did not make this up. This is a very common type of symbol used in math and any other thing that involves logic and things where you're trying to prove things to be true. You're going to make your statements, and then you're going to say therefore. In this case, I'll say therefore the conjecture is false. So you got your counterexample, and when you got your counterexample, you can now say, you're wrong, I'm right, here's why. Long story short, that's basically what you're doing. Okay? Let's do some more here. Alright, 2 complementary angles are not congruent. So if you have angles that are complementary, they can't be congruent. So again, the counterexample, we're looking for a counter. If you want to counter this statement, you got to know what you're trying to do. Okay, if I'm going to counter the statement, I want to say that they are congruent. Now, I don't have to show. Let's see. I can't spell apparently. Yeah, don't have to show that you can spell either, but it helps. Again, we're trying to show they are congruent. What I meant to say is I was writing. I apparently can't write and talk at the same time. But you're not trying to prove that they are always congruent. We don't have anything to prove. We just need to disprove the current conjecture, the current statement, that two complementaries cannot ever, in any situation, be congruent. So if I can come up with an example where they are congruent and they still add up to 90, then I'm going to be good to go. So I'm going to call the measure of angle 1 45 degrees, and the measure of angle 2, you guessed it, 45 degrees. Therefore, if you add those up, measure of angle 1 plus the measure of angle 2, you get 90 degrees. Therefore, the conjecture is false. It's not true. There's my counterexample. There's my statement. Mic drop. You just proved them wrong. Okay. So counterexamples, again, all you gotta do is just come up with one example. Your example doesn't prove that all complementary angles are congruent. That's not what you're trying to do. You're not trying to prove that to be true. You're just trying to say that two complementary angles don't have to be not congruent. They can be congruent if the right situation arises. So that statement basically is just trying to show that it's false, which it is. Alright, now we got a set of data and we got a statement based off of that data. So now we have our data, we just have to look at it. But this one says the monthly high temperature in Abilene is never below 90 degrees for 2 months in a row. So there's your statement and your conjecture. What are we trying to do to prove it to be wrong? Well, we want to know, when is it 90 degrees? Well, below 90. When is it below 90 for 2 months in a row? Again, can't spell, but I'll fix that. Okay, so let's look down here, see if we can find it. Here I got a 88 degrees. Here I got an 89 degrees. So we got our statement, or our data I should say, that contradicts the conjecture that says the monthly high temperature in Abilene is never below 90 degrees for 2 months in a row. So based off of this data, I can say therefore the conjecture is false. So again, as long as you know what you need to do to provide a counterexample, it's pretty easy to find for the most part. Okay, I had to show, they said it was never below 90. I showed that it is below 90 for 2 months in a row, and therefore you're wrong. Okay, so again, just 1 month doesn't count, but you could have, at this point, if you wanted, it depends on if this was last year or not. I mean, in a way, you had December, January, February. It was kind of 3 months. They just, they didn't write it this way, so I was kind of afraid to pick that because it wasn't necessarily consecutive because, beginning of the year, end of the year type thing. So I went ahead and just used January, February to prove that conjecture false. Okay. All right, next up we got same question. Show that the conjecture is false by finding a counterexample. So here we go. For any real number x, x squared must be greater than or equal to x. Now this is a good one because you see this statement and at first you think to yourself, well, x squared is always greater than x. Yet why am I asking you a question asking you to prove it to be false? Well, the reason is it's not always true. So again, this is where we actually get into some good examples where we get these statements that you think is true, but if you really delve into it and try to find a counterexample, you'll see that it's not. And that's why we don't just take statements at their face value. Just because you think something is true doesn't mean that it's true. You have to prove it to be true. And this is one of those examples. So you need to try to come up with some examples where x squared is not greater than or equal and this is again going to be our counter, we need to find a time when x squared is less than x. Okay? Can't be equal to, because it can be equal to an original statement. So otherwise I'd call it 0. Would be good. So you may say, okay, let's use a negative. Well, like negative 2 squared is actually still 4. So that would work. What we need to find here to get a counterexample is something like this. I know you try to avoid fractions, but you can't here because that's where your counterexample is going to come in. So if I found if I said x is 1/2, x squared would be 1/2 squared, which would be 1 squared over 2 squared, which is 4. Now if you'll see here, x squared, which is 1/4, is less than 1/2. So I've just proved that statement to be false if I have fractions, and the fractions have to be greater than 0, less than 1. But again, this is not a proof. I can't say this all the time. So therefore, and you say this a lot, the conjecture is false. As much as it looks to be true, it's not. And that's why we have proofs. You don't want to start going around saying this is always going to happen, and the next thing you know it doesn't. Okay, you have to be able to prove it if you want to make statements, bold statements. Alright, next up, supplementary angles are adjacent. Okay, now this one, you can almost just use the definition. By the definition of supplementary angles, two angles must have a sum of 180 degrees. There's nothing here that says that they have to be adjacent. Therefore, a counterexample would be something like this. Let's say this was 60 degrees, and I'll use another angle here, and let's say that's 120 degrees. And those are supplementary because it's two angles and they have a sum of 180 if I added them. There's nothing in the definition that says they have to be a linear pair. They can be a linear pair, but they don't have to be. So because of the definition and the example that I gave, I can still make my statement. Therefore, the conjecture is false. Okay, so again, now we're going to start bringing in definitions into the fray. Okay, so again, we can use definitions. You can use, when we get into using more theorems, you can use previously proven theorems to prove things false. There's lots of different things that we can apply. Just normal logic, number sense that we use on some of the ones that we've done earlier. Common sense on some of the ones we've done earlier. It's sometimes easy, sometimes hard to come up with these counterexamples depending on the situation. Alright, next up we show have data with planets' diameters, and it says the radius of every planet in the solar system is less than 50,000 kilometers. So again, same thing as we did before. We got your conjecture. Now we are trying to find a counterexample to this conjecture. So the radius of every planet in the solar system is less than 50,000. I'm trying to find something greater than 50,000. Okay? So if you look again, the radius of every planet in the solar system is less than 50,000 kilometers. Well, I mean, look, yeah, we got less than here. That's good. Less than, less than, less than. However, and then we got Neptune, less than, but we got Jupiter, we got Saturn, we got Uranus. These are all counterexamples. So I have multiple counterexamples. You can use either one. You don't need all three. But once you found one of those three, you can make your statement. Therefore, the conjecture is false. Like I say, overall, this isn't so bad. You know, once you understand what we're trying to do, you just need to look at each scenario individually. And again, sometimes it doesn't look like we're doing math. Yeah, I admit that. Based on what you know of math, this isn't math. But you don't know everything about math at this point, this is actually a huge part of math, more in the higher end and higher level thinking, but it is a huge part of using your logic and reasoning skills. So we are still in math, believe it or not. Okay, so we do have a lesson quiz that goes along with this lesson, so make sure you work through this. Okay, so again, especially with Mr. Patrick, again, Miss Moore can do it differently. She'll tell you what she's doing, but I'll check either the lesson quiz or I'll check the notes. So make sure that you have that done, as well as your notes. Again, we got our assignment time. Okay, so again, make sure you understand what you're doing. Again, if you're Mr. Patrick, I'll tell you what we're doing in class, so don't worry about it. But what you do need to do is make sure you scan the QR code, give me a reflection of this lesson, and again, obviously, I'll see you in class. Good luck.